Okay, we're going to look at an intergalactic problem, an IGP, from the Chapter 10 Fluids. We're going to look at number 6 here. And this intergalactic question is, how high up could you pump a column of water? What is the maximum height that you could pump it up? Okay, here on Earth, that is, here on Earth. So if we kind of think about this, imagine that we have a bucket of water. That's water. And we just want to put like a very long straw into it. We want to see how high up the straw we could get the water to go at maximum. Okay, so what is that max height? What we have to do is we first have to think about how straws work. The way a straw is actually working, or a pump is working, is you are creating a low pressure up here, and since there is outside of it an atmosphere, which is a high pressure, this high pressure is actually going to be pushing on the water. Since the water is incompressible, it needs to move somewhere. Now, if you didn't have this low pressure situation up top, the high pressure would be pushing here as well, and you just wouldn't get anything. It'd all be equal. But since you have this low pressure region, as this high pressure is pushing down, it actually pushes the water up the tube. That's what happens there. And then we get the water to rise up. Now, the lowest pressure you could ever hope to possibly create, and let's say that you do it, would be 0. But what we have to recognize is that as we get this depth of water in and of itself is going to create a pressure beneath it. Remember, the pressure due to a column of some fluid is rho g h. And hey, look, we've got a max height we can play with. If we can get the pressure of this column of water to be equal to the high pressure, that means the pressure from the water pushing down and the pressure from the atmosphere pushing up are going to be equivalent. And then we can figure out, well, how high is our water or other fluid going to be. So if we wanted to do this, our pressure here is 1 atmosphere, and if we put that into reasonable units, pascals, or bars, that's 1.01 Pascal, or 1.01 times 10 to the 5th bars. That needs to be equal to rho gh. Now, the density of water is 1,000 kilograms per meter cubed. Gravity here on Earth is the good old 9.8. And we're hunting for a height. So that's it. Our problem's done. We just need to do a little bit of math here. So let's take 101 times 10 to the 5th, divide by 1,000, divide by 9.8. And when we do that, it looks like the maximum height we could pump anything to is 10.3 meters for water. That's a column of water. That happens to be about 30 or so feet. Given about 3 feet in a meter, about. So if you wanted to pump water up, here on Earth, you can go up 30 feet. Then you're stuck. So what a lot of times we do is we pump the water up, hold it somewhere, and start a second pump. And this is actually how they pump water out of coal mines and other kind of mining institutions. But it is a kind of lengthy process. But that's what's going on for problem number 6 there. Now, a kind of interesting thing to take this forward a little bit is if you did a column of mercury, how would this change? Well, if you were doing a column of mercury, your density of mercury, which, let's see, what's the mercury atomic symbol? Mercury. Hg, duh. I'm just gonna, I guess it's proper to put Hg. How did I forget that? Oh, I know how I forgot that. Because I'm a physicist, not a chemist. So density of mercury is actually much, 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 much more than water. While water is 1 gram per centimeter cubed, mercury's, according to the internet, 13.7 grams per centimeter cubed. So 13.7 grams per centimeter cubed. And let's see, that would be 13,000-ish, right? Kilograms per meter cubed. Now, what you'd be doing with a meter cubed of mercury is beyond my reason, but you know, if you had a nice barometer or something, there we'd go. Okay, so we could just shove this in for mercury. We'd get a different height. As you can see, it'd be much shorter. That's just because it's going to push down a lot easier. Now, another interesting thing we can think about for this is, would the height change if you had a different cross-sectional area of your tube? So instead of having this kind of thin tube, would it change if here's our bucket, we had this like super wide straw, like a big gulp straw or something like that? I still remember whenever they put big gulp straws on Capri Suns, and those were a big deal. We were like, whoa, sweet straw. Would this change the game? And the short answer is no. No, it wouldn't change the game at all. You'd still have the same height of water. Everything would still work out the same. The easy kind of quick way to think about this is that whenever we look at a column of water's pressure, this doesn't have cross-sectional area in it anywhere. It doesn't matter. When you go to the bottom of the ocean, it does not matter that there's a mile of water east of you and a mile of water west. What matters is the water above your head, the water above that column. So this is what matters. Okay, all of these columns up and down, and it's that direct height that matters. The fact that it's wide or thin, nobody cares. Nobody cares at all. And we've kind of seen examples like this when we played around in the PhET lab, where they were showing us like you've got some land mass and it's split up, and it's like, oh, but what happens when this is your land mass, and this is the water? Well, the water just, it does its thing. Pressure's pressure, and as long as that pressure is constant or equal on both sides, you're fine. It doesn't matter the openings, it just is a pressure issue. So that's an important thing to keep in mind. It's kind of a weird like non-intuitive thing, because you think with a wider opening it should drop, but that's wrong. Pressure's pressure, and it's just pushing on everything equally. So if you did have a larger opening, nothing would change there. So with that, this intergalactic problem number 6 for the fluids is finished.